Hello everyone, today we are going to explain the basics of OSPF. First, let's talk about why we need to use dynamic routing protocols. Previously, we have explained static routing. To you. Static routing requires us to manually configure and maintain it, but we say that although its commands are relatively simple. However, it has the following issues. For example, it is mainly suitable for small networks or stable networks that do not change easily. If the number of devices increases, the configuration work will also increase, making it very cumbersome to configure. Secondly, if there is any problem with the network, for example, if there is a change in my network topology, my network cannot automatically converge, and I have to manually adjust it. In this context, we say that the routing table, as we discussed before, is divided into directly connected, static, and dynamic. Directly connected means you first need to assign an IP address to the interface, and both my interface and the opposite interface must be up. Only in this double up situation will it generate automatically. For static, you need to manually specify the destination network segment, the next hop address, etc. on the device. When there are many devices, it becomes quite troublesome, and it cannot detect remote failures. For example, if I am supposed to take this route and it breaks, or encounters a problem, I have to manually switch to the route below. On one hand, this involves manual switching. On the other hand, for instance, during this process, here I have a router. Here is another router, here is yet another router, and here is still another router. Now, during this process, if I connect these devices together, labeling them as 1, 2, 3, and 4 during this process, if there is a problem with the link here, but this one will still send to RR according to the static route. If a static route is also written, it will still send to R3. It will not switch on its own at all, nor will it sense a remote failure and choose a different path. It will always take this route. It's quite rigid. As long as it can reach its next hop, it will take effect, and once it takes effect, it will follow this path. If we want to achieve automatic calculation here and perceive remote failures, we need to choose a dynamic routing protocol. So, what about dynamic routing? In our phase 1, we will learn about OSPF, which is an interior gateway routing protocol. Additionally, we have EGP here, which is an exterior gateway routing protocol. How do we distinguish between interior and exterior? This is where the AS autonomous system comes into play. Within an AS, the same IGP protocol will be running, for example, within a company. Large enterprises operate an entire network based on OSPF, so within a company, OSPF is generally used. If we are talking about an operator, they would use ISIS for networking. And in this process, when communicating between two ASEs, we run the BGP protocol, which is the External Gateway Routing Protocol, EGY. If we classify it, according to its mechanism and algorithm in the future, different routing protocols have different algorithms. For example, in this context, RIP is our Routing Table Transmission Protocol, known as a Distance Vector Routing Protocol, while OSPF, when calculating, is called a Link State Routing Protocol. If it is our Distance Vector Routing Protocol, now, the routers running this protocol will periodically broadcast, exchanging our routing tables through routing. So, in this context, for example, our R1 receives a routing table sent by others. For instance, initially our R3 has an address of 3.3.3.3, and then, in this case, he will add 3.23.3.3 to his own routing table and send it to one of his neighbors. After the RR receives it, the first step is to collect it, and after collecting, the second step is to calculate. That is to say, I will summarize both the other party's table and my own table. After calculating, I will send it to the other party. Overall, we need to wait for him to calculate the table first and then publish it. So, after saying it, he also does it. The first step is to collect the table, and the second step is to calculate the table. Then, if there are other neighbors, they will publish it. During this process, each intermediate device does not know where the destination is or how far it is to the destination. They only know that this thing was passed to them by R. They do not understand which device this thing originally belongs to, which means they lack a certain understanding of the overall network situation. What about other devices' understanding of the network situation here? Well, they are unclear and unaware. And what is its fatal flaw? It can transmit a maximum of 15 entries. What does 15 entries mean? Passing through one router counts as one entry, so passing through two routers counts as 2 entries. In large enterprises, it's impossible for the network to only have 15 devices, so gradually, it has been phased out. In enterprises now, they are using OSPF. which is different from our distance vector. Here we use link state routing protocols. For example, OSPF advertises link state information. What is it not? It is not our routing table. Here, it's like I'm giving you pieces of a puzzle. I tell you, hey, this is who I am and this is what I have. Then you calculate it yourself. Oh, I see. Earlier someone, for example, let's say they are called 3. They have this route. I list out a table myself, which is like telling you the locations of all the attractions, and you decide for yourself. You prioritize which attraction to visit first, and then which one next, giving you an understanding of the entire network. You have a comprehensive understanding and know that you can choose the route yourself and calculate it. When we run our link state routing protocol, these devices establish what is called a neighbor relationship, exchanging the link state database with each other. And our link state advertisements. Now, during this process, you see, the link state advertisement information we talk about is not a route. It's something like a fragment. We say that I can slowly piece it together based on this LSA, and within this LSA, it describes the interface status information in my routing table, and for example, the cost value of this route, and the name of the interface I am connected to. I will inform others about who I am connected to and who I am. So what about each device? Each device will generate an LSA to describe the status information of its directly connected interfaces. The LSA will include information like who I am, what I have added, the bandwidth of each interface, and the cost. When other devices receive this, they will send a copy to others through the OSPF interface I am running. This action is called flooding, meaning that like a flood, a copy is sent to all interfaces except the one it came from. First, send it to others, then I will calculate, which makes the flooding process a bit faster. In this context, after receiving data, a copy is sent through other interfaces. Each device running OSPF will establish a relationship called a neighbor relationship through a type of message called a hello message. Other routers running OSPF will receive this LSA, and store it in a specific place. Store it in the LSDB, and one of its advantages is that I don't have to wait to transmit the table or calculate the table. So, in this context, I can directly first, we complete the table transmission, then I calculate the table to speed up its synchronization. Moreover, here we calculate the routing based on its bandwidth. Based on its physical bandwidth, and if a problem occurs, unlike static routing, I won't be unaware of the switch. I will automatically switch. Actually, the core of OSPF is to let each device know the real topology, and perform its own calculations. Now, after obtaining this LSA here, I will put everything into the LSDB. Each router generates this LSA, and when I receive my own data, right? After receiving it, I will put it all into my own LSDB, the link state database. The router uses this database to learn the entire network's topology. In this context, the link state database contains all the devices in the current network. All routers, their interface descriptions include the entire network. It's an introduction to the topology. First, in this process, once we know it's in my table, I put it in my table, and then I directly start doing what? I directly send it to my neighbors, to other neighbors connected to me. After sending it, I proceed to calculate, and each router will use this in the process. The shortest path. First, SPF algorithm and the information in our link state database are used to calculate the routes. Then each device, each router, calculates the shortest path to a destination from itself. For example, during this process, it will calculate, hey, what is my shortest path to 1 PAL? What is my shortest path to 4? Or, if we take 1 as the root, and perspective, it will calculate, hey, what is my shortest path to 2, my shortest path to 4, and my shortest path to 3? To determine a loop-free shortest path tree with itself as the root. Through this tree, a router can determine the optimal route to every corner and every device in the network. In this context, it is a loop-free calculation of the shortest path. For instance, everyone probably has a mental map of the shortest route to the office, the shortest route to a friend's house, or the shortest route to school. The SPF, or shortest path first, is the core algorithm of OSPF, used to select the best path in our complex networks. After calculating this path, which we consider the optimal route, we place these optimal routes into our routing table. Future forwarding is then done according to this routing table. In this context, each device will add the routing table to its own global routing table for future forwarding. The first step here is to establish neighbor relationships. To establish these relationships, we must ensure that our devices can connect with each other, as this relationship is crucial for subsequent synchronization. For example, what if if you want to bring two people closer together, the first step is for them to get to know each other and establish a relationship. In this context, the relationship being established is the neighbor relationship. Once the neighbor relationship is established, we then exchange LSA's link state advertisements with each other. The link state advertisement LSA information is like saying, hey, let me introduce myself. Who am I? How many interfaces do I have? Here, what is the bandwidth of each interface and what is the cost? Who are my neighbors? Each device has its own LSAs, and they exchange and synchronize these with each other. During this process, I store them in my database, the LSDB, Link State Database, to keep my information. It's similar to a map, where everyone has their own. For example, a map to school or a map to the company, but the starting points are different. Let's say we're all going to the company, each starting from our own home. To calculate the shortest path, here it uses an algorithm in our network called the SPF, shortest path first algorithm. A method to calculate our routing table. If during this process, the route we calculate is a tree without loops, then after calculating it, we take this optimal route and add it to our routing table. This is the process by which the link state routing protocol is implemented. So what are the advantages of OSPF? OSPF is a typical link state routing protocol. It is also the most widely used in enterprises today. Among them, OSPF v2 is specifically designed for IPv4. And in the future, you may encounter OSPF v3, which is designed for IPv6. Unless otherwise specified, when we refer to OSPF here, we are talking about OSPF v2. We say that OSPF routers exchange link state advertisement information, but they do not exchange routes. What they exchange are LSAs. The link state advertisement information is a key piece of information for OSPF to perform topology and route calculations. By collecting these link state information from the network and storing it in the LSDB, routers can understand the entire network topology and design loop-free paths. Each router uses the SPF algorithm to calculate the shortest path to the destination. Based on this, it generates routes and places them in our routing table. It supports VLSM and summarization, as well as the multi-area route calculation, and that is our OSPF. If anyone wants to learn Huawei certification technology or obtain Huawei certification question banks, please send a private message. I can also leave more comments below the video for technical exchanges.